Now, this is one of my least favorite topics in calculus, not because I think it's hard or anything, because it isn't. I don't like it because it shouldn't be a topic to begin with. All you need is a basic understanding of derivatives and the chain rule to dominate this concept. And here's what I mean. We should know by now that the derivative of x with respect to x is equal to 1 because you're comparing the growth of x with respect to x. You're comparing the growth of x relative to x, and that's just always going to be 1. But, let's say we're taking the derivative of y with respect to x, or the derivative of some variable with respect to another. Well, that would just be the derivative of y with respect to x. That wouldn't reduce to 1 because we don't know what their growth rates are. We haven't specified it yet. Similarly, if we were taking the derivative of r with respect to x, that would be dr dx. And then next, if we had the derivative of s with respect to s, so the derivative of s with respect to s, that would reduce to 1 because you're taking the derivative of some variable with respect to that same variable. And one more time, I'm going to just overemphasize this. If we have the derivative of z with respect to s, well, again, you are comparing the growth, so you're looking at the rate of change of z with reference to s. And yes, that would still be the derivative of z with respect to s. So here's what I mean, with that basic understanding of the derivative. Now, let's go ahead and take a look at the following. Let's take a look at the chain rule now, just as a quick reminder. So if we had the derivative with respect to x of, let's say, a composition, f of g of x, we've seen this time and time and time again. Well, again, we would go ahead and take the derivative of the outside while leaving the inside the same, and then multiply by the derivative of what was the inside, which would be g prime of x. So the derivative of g of x would be g prime of x, and then you multiply by the derivative of x. With respect to what? Well, we were taking it with respect to x. And yes, again, this would reduce to 1 in this situation, but in further situations, we need to be okay with being exposed to these different letters and variables because we won't always take the derivative with respect to x. I'll be real with you right now. In real world situations, when it comes to the next chapter, you'll begin to take the derivative with respect to time, along with other dimensions, like taking the derivative with respect to a radius or a side length or something else. And that's what the next chapter is, applying that derivative to real world situations. We won't always be working with a graph on our paper. We will begin to apply this to the real world. And so the reason this topic might confuse you now is because, you've been taking derivatives, quote, explicitly up to this point, most likely. And here's what I mean by that. What I mean by explicit differentiation is when y is already there for you. It's already by itself. So let's say we were asked to find the derivative of y with respect to x of the following function. If y equals 3x squared, all right? Y is already isolated for you. So there's no need to think about the emphasis of the chain rule or worrying heavily about the notation because, it's just there. Y is already there. So if we were to take the derivative of both sides with respect to x, that would be dy dx equals, then you take the derivative of 3x squared, so that would be 3 times 2, so that's 6x to the first power times dx dx, so that'd be 1. So it would just be 6x. And here, look, the dy is already isolated for you. That's what explicit differentiation is. Implicit differentiation is when y isn't already isolated for you. So, for example, let's say we were looking at, find the derivative of y with respect to x if our equation was, x squared plus y squared equals 9. Now, let me just go ahead and erase everything. That way I can just rewrite everything so I have, all the space I need to explain this. So, again, we're trying to find the derivative of y with respect to x if y, or if this equation was the equation we had. So if x squared plus y squared equals 9. So I'm going to go ahead and erase this down here now. All right. So, if we're going to find dy dx, look, all we're doing is just taking the derivative with respect to x of both sides. That's all you would do. So you would just take the derivative with respect to x of, the entire equation, which means that you would take the derivative of one side and then take the derivative of the other side. So let me just go ahead and overemphasize that right here. So then equals the derivative with respect to x of 9. And there we go. And that's what that's what this means we'll do. This is all implicit differentiation is. You've always been taking the derivative with respect to x of both sides whenever they ask you to find dy dx. But now this is just a situation where y isn't already laid out pretty for you. That's all it means. So please don't let the term or phrase implicit differentiation scare you in any way, shape, or form. So what we're going to do is just follow our rules of differentiation. Really, it's all we have to do. Trust the process. So remember, we're taking the derivative of a sum, so that just means take the derivative of the first plus the derivative of the second. All right, so if we're taking the derivative with respect to x, I'm going to overemphasize everything here, guys, so pay attention. The derivative of x squared with respect to x, that would be 2 times x times dx over dx. Again, remember, because we can treat this like something squared, so a composition. So if we're taking the derivative of something squared, that would be 2 times that something raised to the first times the derivative of that something with respect to x. Next, the derivative of y squared with respect to x. Again, chain rule. It applies every single time. So we have something squared. Again, the derivative of something squared is 2 times that something now raised to the first power multiplied by the derivative of that something with respect to x, or dy dx this time. Next, we're taking the derivative with respect to x of a constant of 9. That always reduces to 0 because constants do not have a rate of change. They have a rate of change of 0. They do not rise nor fall. Boom. So there we go. We're good so far. Now, this is it. We're done. We are done. In implicit differentiation, your first step is calculus. Everything that you do from here on out is just simplification. It's just algebra. You're just making it look pretty because they want you to find the derivative of y with respect to x isolated. So that's what we're going to do next. We're going to isolate it. So let's take a look here. Dx over dx, again, this reduces to 1. There's nothing else that'll reduce here, nothing else at all. So we're just left with 2x plus 2y dy dx equals 0. To isolate the dy dx, we can treat it like its own variable. We're just trying to isolate this variable. So first, we see that we have an extra term. So subtract 2x from both sides. Then afterwards, we'll need to divide 2y from both sides. So first, like I said, subtract 2x from both sides. Over here, over here. So this means we'll be left with 2y dy dx equals negative 2x. And then, like I said earlier, we'll be dividing 2y on both sides, which will give us, I'm going to write it over here, which will leave us with dy dx equals negative 2x over 2y, which reduces to negative x over y. Now, here's just, some collateral damage with implicit differentiation. Most likely, your answer is going to include 2 variables. Here, we have x and y included in the derivative of y with respect to x. That is completely fine. That is completely fine, guys. Do not worry about that. Your answer can be in this form. In this specific situation, we could solve for y first and then take the derivative explicitly. And here's what I mean. Let me go ahead and just change the colors. Let's go ahead and say orange. And again, we're trying to find dy dx if x squared plus y squared equals 9. All right, I'm going to go ahead and calculate y first. I'm going to, solve for y and then take the derivative explicitly. All right, so here we would subtract x squared from both sides, giving us y squared equals 9 minus x squared. And then we could take the square root of both sides, leaving us with y equals the square root of 9 minus x squared. All right, cool. So here we go. We just solved for y. Now, let's take the derivative with respect to x on both sides. So dy dx, that's the derivative of y, equals the derivative with respect to x of the square root of 9 minus x squared. Again, guys, so now we need to go ahead and pay very close attention because here we're just going to apply the chain rule. There's 2 levels. We have the square root of something, and that something happens to be 9 minus x squared. Remember, the square root is the same as stating, that we have something raised to the 1/2 power. That is what the square root is. We have something to the 1/2 power. And so if we're taking the derivative of something to the 1/2 power, well, that derivative that derivative will be, well, drop the power, so 1/2 times that something. Then you subtract 1 from the power, so 1/2 minus 1 is negative 1/2. Use a calculator if you doubt me. And then you multiply by the derivative with respect to x of what's left on the inside. So 9 minus x squared, so that constant will be 0. Negative x squared, the derivative of negative x squared would be negative 2x. So multiply by negative 2x. And then afterwards, because we have something squared, that would be multiplying by the derivative of something, or the derivative of x with respect to x, that would be 1. I'm not going to be redundant in this video. So let's just go ahead and take care of that right there. All right, cool. And then finally, we can simplify if we want, because a negative 1/2 power means we're dropping it to the denominator. We can leave that 1/2 as is. But notice we have 1/2 and then a 2 here. So actually, we can just go ahead and reduce it right now. We can reduce it right now and save ourselves a little bit of trouble. And then, so that 9 minus x squared raised to the negative 1/2, that's the same as the 9 minus x squared to the positive 1/2 power in the denominator, which is the same, like we said earlier, as the square root of 9 minus x squared. And so we're left with negative x in the numerator. So let me go ahead and just erase this here. And that would just be a negative x in the numerator. This looks very, very familiar. Let's take a look at right here. So we saw earlier that the derivative of y with respect to x was negative x over y. Well, if we wanted to, we could replace y with what y actually is. Remember, we solved for y earlier. We found that y is equal to the square root of 9 minus x squared. The same thing. The same thing, guys. So let's just go ahead and try to wrap our heads around this. So, implicit differentiation is just taking a derivative when the variable that you're taking the derivative of, or what you're trying to find, it just isn't isolated by itself in the very beginning. It just isn't there for you to just take the kill shot. You're just going to have to take the derivative implicitly. In this example, it was possible for us to essentially, isolate the y and then take the derivative. It was possible for us to derive this implicitly or explicitly. What explicitly means when it's isolated. But there are too many situations where you are not able to, find y by itself, or whatever the variable is by itself, before you take the derivative. And so a lot of the times it will be necessary to just simply take the derivative without isolating the y. And trust me, more often than not, it's actually a lot easier to just take the derivative implicitly than trying to make everything look pretty. And so let me go ahead and erase everything. That way we can begin a new example. That way I can emphasize what I mean when I say that, we can't just isolate the y all the time. Let's go ahead and say we have the equation x times the sine of y equals 3y. And we're asked to find the derivative of y with respect to x if this equation holds true. So if x times sine y equals 3y, let's go ahead and calculate dy dx. Right out of the gate, notice isolating y will be a tall order. There is really no reasonable way for us to find y by itself, or isolate the y, so we can take the derivative explicitly, where y is just by itself. And so again, guys, as long as you have a basic understanding of derivatives and the chain rule, with notation and all that good stuff, you're good. You are good. Just take the derivative implicitly, or just take the derivative. You're still just computing the derivative. Implicit differentiation just means that you're taking the derivative even though y isn't by itself. That's all that means, and it's completely okay for you to do so. So let's go ahead and go through this example. We have x times sine y. We have a term multiplied by another term, and both of these terms include a variable. This is the product rule. X times sine y. This is a product, and the terms have a variable. We will utilize the product rule. Remember, the product rule, if we have f times g, the derivative is, so the derivative of f times g would be f prime times g plus g prime times f, or the derivative of one times the base of the other plus the vice versa. Just a quick reminder. So here, let's just go ahead and do our thing. If we identify x as f, sine of y as g, well, let's go ahead and find out what f prime would be. F prime would be, well, just 1. since we're taking the derivative with respect to x, remember, derivative with respect to x, it will be 1 times dx over dx, which is still 1. Next, we have g equals sine y. So let's just say g equals sine y. And so g prime would be, and remember, we're taking the derivative with respect to x. We have sine of something. The derivative of sine of something is cosine of something. And then we multiply by d over dx of the input. So that would be dy over dx. And I hope this makes sense. I really do hope this makes sense. Because next, we're just going to go ahead and just put it all in. Remember, f prime times g. F prime is 1. G is sine y. So that would just be sine y. Plus, well then the opposite. So g prime times f. G prime was cosine y times dy dx. F is x. So here we would have x times cosine y times dy over dx. Awesome. Up next, we're taking the derivative of the right side now. So the derivative of 3y. Well, let's think about it. We're taking the derivative with respect to x of 3y. Well, remember, the derivative of a constant times a variable is the constant times the derivative of the variable. So we can essentially pull that 3 out and say that this is equal to 3 dy dx, or 3 times the derivative of y with respect to x, which is completely fine. 3 dy dx. Again, like I said this before and I'll say it again. Implicit differentiation, just like any other differentiation problem, the first step is calculus. The only reason implicit differentiation is special is because afterwards you just need to go ahead and utilize basic arithmetic and algebra skills to isolate dy dx. Notice in this situation we have 2 of them. We have one here and one here. Don't be afraid, guys. It's not that hard. Here's what I'm going to say over here. Let's say we were trying to isolate x and we had, 3x plus 2 equals x minus 5. If we wanted to isolate x, well, all we got to do is just move things over. Because then we would have 2x. Then we would subtract 2 from both sides. So it would be 2x equals negative 7. Then you divide both sides by 2 to get rid of everything else that's attached to the x. We've done this more often than I can count to 2 in my sleep. I can count to that all the time. But you guys have done problems like this more often than anything. It's the same concept. Treat dy dx like a variable because it is. It's just a variable. So to isolate it, well, here it would be easier for me, or not easier, but it would take less amount of work to just take this term entirely and essentially, quote, move it to the right side. The reason I said quote is because it's not mathematically proper to say move, but we would go ahead and subtract the entire term to both sides, or on both sides. Dy dx. Not equals, let me just go and erase that. We are subtracting x cosine y dy dx from both sides. This would leave us with sine of y equals 3 dy dx minus x cosine y dy dx. Lastly, like I said, guys, this is just algebra. The first step was calculus. This right here, that was calculus. This is going to be algebra, 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 algebra. So next, what do we do? How do we do this? Guys, calm down. All we need to do is factor out the common term, or the dy dx, because that's why we went ahead and subtracted x cosine y dy dx from both sides to begin with. So that we can group all of the terms that have dy dx by itself, leaving everything else on the other side. So on the right side, and let me just go ahead and rewrite the sine y. On the right side, we're just going to go ahead and factor out dy over dx from both terms, because they both have one, leaving us with 3 minus x cosine y. Awesome. And guess what? We're done. Because all we have to do from here is isolate the dy dx. So that means dividing both sides by 3 minus x cosine y. 3 minus x cosine y. And so on this side, this would reduce to 0. Not 0, sorry. This would reduce to 1, because anything divided by itself is 1. And then leaving us with that on the right. And so our final answer in this case, let me just go ahead and move that over. The final answer in this case would be dy over dx, or the derivative of y with respect to x, is equal to the sine of y over 3 minus x cosine y. Again, guys, I didn't do anything special. All I did was use my understanding of the chain rule along with my understanding of the derivative to just find dy dx. It just took a little extra work, just algebra. That's all it was. It just took a little more algebra. But if you understand the chain rule and understand that the derivative of y with respect to x needs to be included, and that dx over dx always needs to be included, even though it reduces to 1, if you understand that that is necessary, then implicit differentiation is in the palm of your hands. And so this was just an introductory video to implicit differentiation, but I hope this was making a lot of sense. And if it doesn't, don't worry. Check out the next couple of videos on implicit differentiation, because trust me, I will be going over plenty of examples with it, because this is the stepping stone going to next chapter. So go ahead, practice, watch, and master, and I'll catch you next video.